Okay. So as we send the juniors out, here's our situation. And so what we'd like to do, our problem is that Monica is going to drop the rock, and then she's going to hear the sound come back to her. And so what we have to do is to figure out how tall the building is based on this. So I'm going to give you a tool that I use for thinking about this, and that tool is to think about the entire time interval almost like a timeline. So our tool here is the timeline. And this is much like the timeline that you get when you do any video editing. Have you ever done a video and then like edited it later? And so what you've got is a timeline down at the bottom. So we're thinking about the action unfolding frame by frame. And what we know is that the entire time interval is 1.10 seconds. The drop happens here, and the sound comes back here. And what happens in between is the actual hit. Now, why did I draw the hit over on this side? Right, because the sound goes pretty fast, right? But the actual drop, this is the duration while the ball is dropping right here. And this is the duration while the sound is coming back. So actually I've exaggerated. The hit is really very close to here. Let me move that. So our hit really should be drawn about right there. Because it only takes a short amount of time in order to get to the bottom. Okay? Now, I'm going to show you two different ways to think about this problem. The first is the math way. A mathematician wants an exact solution. So the mathematician is going to say, let me divide up my whole time interval here into t, the amount of time that it takes to drop. And that means that the rest of this, the rest of this right here is going to be 1.10 minus t. So t is the drop time, and 1.10 minus t is going to be the sound time, like that. And now a mathematician is going to reason that here's our physical layout, and just for the sake of not worrying about negative numbers, I'm going to take 0 to be the top, and I'm going to take 6 to be the bottom. Excuse me, it's not 6, it's whatever h is, the height of the building. So we're taking down to be plus in this case. And so the mathematician is going to reason that the distance that the rock drops downwards has to be the same as the distance that the sound comes back upwards. And the distance that the rock drops is going to be delta y is equal to v0t plus 1/2 at squared, which is equal to 0 plus, and here I'm going to use 9.80 because I need 3 significant digits of precision. And the rock is going to fall a distance of h under the influence of gravity. And the sound, meanwhile, is going to travel that same distance back up at a constant, non-accelerating rate of 343 meters per second. And now those two distances have to be equal to each other, and so I can set them equal. and I get an equation that is one equation with one variable, and I can solve that equation. First of all, what type of equation is it algebraically? It's quadratic because it has the t squared in it. So I've got some options for solving. I can solve with the quadratic formula. But my favorite would be to solve with the calculator using the second calc intercept. And all of you have learned how to do that in algebra class, right? Yes.
These are the problems we see on the test.
I can imagine doing that because, as we're about to see here, the physicist is going to do this in a more efficient way. This setup is going to give us an exact answer. And then I round that to 3 significant figures. Have all of you learned how to do second calc intercept on your calculator to solve equations on your calculator? Yes, no? Like, if I gave you this equation and said, here, solve this on your calculator, would you be able to do it? No. So you have not learned how to do that. So you didn't do that in Algebra 2? Or Algebra 1?
I think we did it, but I think I forgot how to do it.
Okay, all right.
Are you talking about finding the zeros or the intersections?
Yeah, finding the zeros and the intersection points.
You
Tell you
put
what,
second-
I'll put out a short video to show you how to do that because it's a needed skill. But I want to talk about the other way of doing it because it's more efficient. A physicist is going to reason like this. Here's the physics way. The physicist is going to say, look, the amount of time that the sound is traveling back is really, really small. The sound comes back just like that. So what I'm going to do is I'm going to pretend that it takes no time at all. And I'm just going to solve the problem as if the entire time were the drop time. I know that's not really true, but it's going to give me an approximate answer. And then I'm going, based on that approximate height, I'm going to come back and figure out how long the sound really took. And then I can subtract that off and recalculate my height. That's the way physicists will do it. So here's how this goes. The physics way. Assume that 1.10 minus t is basically 0. So that, in other words, we're assuming that the time is basically 1.10 seconds. And so now I can compute the drop time, which is delta y, which is also equal to h, is v0t plus 1/2 at squared, which is going to be 0 plus a half of 9.80 times 1.10 seconds squared. Now I know that the drop time isn't really 1.1, but it's close enough. And when I do that computation, what I get is 0.5 times 9.80 times 1.1 squared, which is 5.929 meters. I'm going to call it 5.93 meters. Okay? Now, this is our approximate height, assuming that the sound takes no time at all. How long does the sound really take? If I set the distance of 5.93 meters equal to the speed of sound times time, and solve for the time, what I find is that the time that the sound takes is 0.017 seconds. 17 milliseconds. About the same amount of time that you get for a real fast slapback echo. And so I can now use that to change my actual drop time, I'll just finish this up, is 1.10 seconds minus 0.017, which comes out to 1.08 seconds. The actual real drop time is just a little bit shorter. And I can recalculate h equals 1/2 of 9.80 times 1.08 squared. Which gives me 5.71 meters. So notice that Chapelier is actually a little bit shorter if we measure it in this way. I will put this up on Edmodo and you can study it in case you felt rushed.